So I don't know whether this is meant to be the uplifting, optimistic talk to send you all home round the M25 happy that David alluded to. That's a fairly invidious task. So I ameliorated the title that's on the sheets and put in, I'm going to show you or talk about some example technologies that may help in maintaining North Sea production. And I've also undertaken to present some stuff on behalf of some colleagues at Heriot-Watt University, Barman Tahidi and Mike Christie. So again, slowing the decline rather than maintaining the production. Just to recap, the prize is 1 billion barrels of oil for every extra 1% recovery factor across the known reserves of the North Sea. And I'm picking up in particular on, well, various industry and government initiatives have looked at how to improve recoveries, and increased oil recovery, IOR, group has prioritised 10 areas, particularly low salinity water floods, chemical EOR, and low-cost subsea developments. I'll come back to those. But of course, as several people have said that already this morning, that the key is cutting costs per barrel of oil equivalent, so either cutting costs or improving the barrels. So this talk, it's not X-rated, it's not to do with the strength of beer, it's a mnemonic for experience, expertise and extraordinary, picking up on what Paul said, something out of the ordinary, something that's innovative, novel, is what is required is the theme. And I'm going to show 3 examples of that in production area, reservoir development optimization, and then in understanding reservoir mechanisms. So I'm going to go very quickly, unfortunately, through Barman's piece. He's an expert in flow assurance and hydrate inhibition. And Heriot-Watt have formed a spin-out company on the back of his technology that is, rather than the conventional way of injecting hydrates for pipelines, that avoids the hydrate phase envelope completely, the HydroCheck technology does something more clever. And if I skip to this methodology, essentially it's taking downstream aqueous samples and measuring the electrical conductivity and the acoustic velocity in those samples, and backing out, inverting from those the concentrations of salt and hydrate inhibition in those samples, and with also with the hydrocarbon composition. It goes through a thermodynamic model to a hydrate safety margin. So rather than avoiding the hydrate phase altogether on this pressure temperature plot, one can begin to delve into the places where hydrates will form, but only after certain times, and you can sort of ride the curve a little bit there. So very quickly, this has been proven in the Middle East and also in the Nuggets gas field, a small gas field in the northern North Sea, where there's 5 subsea wells, gas wells, and 2 subsea manifolds with a 40-kilometre line to the Alwyn North platform. So there's a story there about cooperation, perhaps, but that line is obviously susceptible to hydrate formation. This is the production profile. Small production, 200 million scuffs a day, declining with fairly low water production up until 2010, when water coning occurred on one of the wells. And at that point, the methanol requirements for hydrate inhibition were beyond the storage and injection capacities of the platform. And so the conventional thing would be to decommission, but this hydrocheck technology, various studies, but this was central in extending the field life through the high water cuts that have been happening, producing an extra 2% of recovery. A small example, but one where innovation can help. And reading this, you can read more about it on this SBE paper, but one quote from it that I liked is that the operator buy-in was a key to trying something new. So turning now to Mike Christie, he presented on this here at one of these events in November, and he's picked up on optimization algorithms from computer science. I won't even attempt to describe what these are, but they're being applied to history matching of reservoir simulators to produce multiple models with associated probabilities, and they also to optimizing field designs amidst the uncertainties. So another example, a small field from the North Sea, subsea again, and here the exercise was to, it's a what-if exercise, but it has been applied in anger, so to speak, but not on this case. The multi-objective optimization, trying to maximize the cumulative oil whilst at the same time minimizing the maximum water rate and optimizing on the variables of well locations, injection well rates, for producers and for injectors, and the status of the injection wells, so they're either on or off. So these four clusters in this cumulative oil production versus maximum water rate, these five clusters are 0 and 1, 2, 3, 4 injectors on stream. And this picking up on two of these models, which are sort of high oil production, but different water rates. This is with 3 producers and 2 injectors, whilst this second cluster is with an extra producer and an extra injector. It's got an extra producer because in this case, the optimization put the producer outside of the active field area. So one can then, with this sort of exercise, one can begin to look at these optimum points and do economic trade-offs as to you can get an extra 10 million barrels or reduce your production by 10 million barrels, but you've got less water capacity, water handling, and 2 fewer wells in the Model 1. So it's one can begin to look at economic questions of that sort. Just the pictures of the oil saturations, I won't go into that. On my home territory here, looking at reservoir mechanisms and understanding those, so I've looked over a fair significant part of my career at whether the equations that are in reservoir simulators are sufficient, and it's been my conclusion that they're not, that there are other things going on than are envisaged in the eclipses of this world. And these are to do with geomechanics, with microcracks which are stress aligned. These microcracks are at densities at which they're beginning to interact, their stress fields are interacting, and that gives interactions over long ranges, and that they're very sensitive to production-induced stresses. They're not, as I say, included in conventional reservoir simulation, but they have strong commercial implications for both secondary and IOR floods. So, and that's in terms of flow directionality, which directions through the reservoir injected fluids are going to move. And that has a knock-on effect for sweep efficiencies and oil recovery. That then tells you things you would like to do with your well configurations and the numbers of wells, particularly injectors. what water production, and particularly its timing, and water injectivity, filtration requirements, etc. As I say, these interactions can be long range, and that then provides a means of interpreting fault and fracture flow paths mapped across fields. I'll just say very quickly, this is a histogram of crack densities that have been, in the red curve, have been interpreted from observations of shear wave anisotropy, shear wave splitting, by Stuart Crampin. And there's a strong peak in the number of cases around about 0.05. These are dimensionless crack densities. And that happens to be the point at which these elastic fields around cracks tend to interact with each other, and it's rather like magnetic fields around spinning electrons. They begin to interact and can interact over large distances at this critical point. And it's a different critical point from that of crack intersection, which has hitherto been thought of as the cause of long-range behaviour. One does see long-range behaviour in the shear wave splitting. It's responsive to earthquakes taking place tens of kilometres away. I'm sorry I'm going over this very fast, but so what does this mean for flooding? It means that as you start to inject in wells, you can get dilation of these cracks, microcracks, and that dilation is in particular directions, about 30 degrees to the crack strike or the maximum horizontal stress. But although that's where the dilations are occurring most, the individual cracks themselves are aligned still with the SH max direction. So within that situation, one expects the flooding directionality to be aligned more or less with these cracks. It's taking them towards that direction because that is the anisotropy of the permeability. And what do we see in the field? We see this is a collection of studies, collection of fields studied some time ago, where these peaks in the frequency of fields in which the directionality of flooding is very close to the SH max direction, at about 10 degrees from it. So generic trends then in flooding directionality. Earliest water breakthroughs along that SH max direction or the crack strike direction. These tensile fields are interacting most along that 30-degree direction where you might expect to see permeability increase as well as pressure support. Along the orthogonal direction, you've got compressive stresses tending to close cracks down, and the pressure support will only be able to take place through hydraulic movement through the matrix of the rock. You may in fact see permeability decrease. So the prize in terms of field behaviour, it makes a big difference whether you get your well configuration, your well pattern correct relative to that directionality. If you get it favourably aligned, you can see a big difference in the aerial sweep efficiency to breakthrough of water. You will eventually get to the same sorts of sweep efficiency if you're unfavourably aligned, but it'll take a lot longer to get there, and at higher water cuts. And in the meantime, you've saved all that water production. You may in fact not be able to get there because you haven't got an artificial lift to get the oil production, and you've got all that water to handle. So not only lower water cuts, but you're probably increasing oil recovery, increasing the oil rates, and potentially fewer wells, particularly injector wells, by configuring your floods relative to this directionality correctly. This was some field data which tends to support that idea. producing wells which are aligned from the nearest injector well along the SH max direction suffer higher water-oil ratios and lower oil production than in the orthogonal direction. You've got the converse, higher oil production and lower water-oil ratios. These are big differences. This is a field, in fact, in Alaska, but the differences are very large here. How am I doing on time? I've lost track. About 5 minutes. So this is that same field where the stress measurements are shown here, and in fact they rotate from one side of the field to the other through about 90 degrees, something perhaps to do with a fault trend in the basement. And if we look at these stress measurements in orientational distribution and look at correlations in rate, fluctuations in rate being correlated between pairs of wells, then one sees again these correlations switching in the same direction in the same manner as does the stress observations. So from one side or the other, almost orthogonal behavior. Now the field development in this field the pattern was a line drive, a north-south, chosen without any of this knowledge available. So if this theory is right, then one would expect somewhat better behavior in this part of the field, because the alignment of these injectors doesn't take water directly into the nearest producer. It's slightly off relative to here, where water would be expected to be moving almost directly to the nearby producing well. So looking at the actual productions up until 50% water cuts in the two parts of the field, about a 14% recovery of oil, initial oil in place in the northeast area, and an 18% recovery in that. One can never do the perfect experiment. One has to pick up on the data that's available, but that's at least consistent with the idea that if you get the alignment correct, albeit fortuitously, it's better, at least in this part of the field, and an extra recovery, some 30% extra recovery at low water cuts because of that, perhaps. There are other factors that may be playing a part, of course. And I'll skip quickly through this. One from these rate correlations, one can infer directions of stress, interpolate between the measurements. That enables one then to put those into a model, a geomechanical model, and infer magnitudes of stress, so that you can look at where there are low stresses. Seems to tie up with where there are high water-oil ratios. Loose and floppy fractures tend to go with water moving through them quickly and giving high water-oil ratios. One can put those stress magnitudes and orientations onto a fault map and assess the conductivities of the individual faults, put those into a model. Here we used a front sim flow stream model because it can take the anisotropic permeabilities, and then look at streamlines and water saturations in one's normal day-to-day reservoir management processes. So, messages rather than conclusions. Slowing North Sea production decline. Expertise, experience, that's motherhood and apple pie, of course, but innovation, very much agree with that. And sales pitch, that PetroMall is offering a one-stop shop. This expertise is available, those that I've talked about, and many more besides, different technologies. Okay, thank you.